Hey, this is Robert Quimby, and I'm going to tell you about photometry. So we've been working with CCD imaging data, and you know that after you've processed your CCD data to remove bias and to divide by the flat, you get pixel values that are proportional to the number of photons that were incident on each one of those patches of the detector. So now what we want to know is how many photons did we get from our source? What's the relative number of photons we got from some source? So the way we do this, of course, is we take all these numbers and we add them all together. And that's photometry. That's the basis of photometry. Now, there's different ways that we can do that, and there's some things you got to be careful of, and so that's what we're going to go over in this tutorial. So we're going to learn a little bit about aperture photometry in this tutorial. There's different types of photometry. We're going to focus on aperture photometry, so we'll describe what that means. And then we're going to actually put this into practice. We're going to measure the number of counts that we get from a certain object in the sky. We're going to have to be careful to account for the background level. Even after we've done processing, there's still background light from the sky, and we have to account for that. We're going to make measurements, so we have to evaluate what our uncertainty is. So we're going to talk about how we can do that. And then we're going to see these AstroPy affiliated packages, a package called photutils, which is actually very helpful in doing circular aperture photometry. So we'll hear a little bit about that. All right, so just a first thing we got to get out of the way is we got to talk about this terminology here. So we're going to be talking about doing aperture photometry. And this is kind of an unfortunate naming scheme that we have because this aperture, when I say aperture photometry, I'm not saying anything related to the size of your telescope. So normally when you hear aperture in astronomy, we're talking about is you have a 1 meter telescope or a 2 or a 10. That's your aperture. How big is your primary mirror? That's not the case here. When I'm talking about aperture photometry, I'm actually talking about the size on the celestial sphere, the area on the celestial sphere that we are measuring light from. So you can imagine putting a circle in the sky somewhere, just on the celestial sphere, and saying, how much light are we getting on that patch of the celestial sphere? That's what we're doing here. Now, this terminology has some ancient origins in astronomy. It used to be the case that people had devices that looked something like this, maybe not quite this modern, and they would attach this to the end of their telescope. So what this has here is there's a little hole here, and this is not a camera in here. This is actually just one pixel detector. So any light that falls within that hole there goes into a detector back there and then is converted into electronic signal, and it goes to some device that reads it out. So the size of this hole here, right? Just like you have the size of your telescope primary mirror, that's your aperture. Well, the size of this hole here is also another aperture, and that's why it's called aperture photometry. So it used to be the case that you could put a hole of different sizes on the back end of your telescope, but in modern photometry, what we're doing is we actually have a CCD on there, which has lots and lots of different pixels on it, and so we get to make a synthetic aperture. We get to decide how many pixels and which pixels do we want to include and do we want to use for our measurements. But we still use the same terminology, aperture photometry. All right, so the simplest thing that we can do is we can just put down a box on our image, just cut out a little rectangular area of our image, and then count how many photons or how many counts we got in there, and use that to measure the brightness of our object. So what we're going to do is we're going to first load in an image. So we're going to use the example.fits from the media folder here. So I'll load that in. And then I just want to show you what this looks like. So I'm going to cut out just a little tiny bit, and we're going to focus on one particular star. It happens to be at the XY coordinates 244, 640. And I'm going to have a margin of 10 on either side of that, top, bottom, left, right. And we're going to cut out a stamp centered on that XY position with that margin, and then we're just going to show it here. So let me run this, and then we can see there's our image down there. Let me run it again so it moves up. So this is the star that we want to measure the light from. This is just the little square that we cut out. And so when we're doing box aperture photometry, we need to do two things. We need to measure the counts from our object, and we also need to get some estimate of what the background is. So this is our target aperture that we're going to measure in, and now we're going to define a background aperture, and all I'm going to do for this is I'm going to define a square of the same size. I'm just going to shift this y coordinate up by 20 pixels. I'll show you why I do that, because this is what that looks like. So I just took a different patch of sky, just a little bit above where our target is, The box is the same size as before, and you can see there's nothing obvious in here. It's just background noise as far as we can tell. So we're going to use this to get a measurement of what the background level is, so then we can see what the total light is in our target aperture, our object aperture, without that background light. So how do we do this? Well, this is very straightforward. If we're using NumPy, all we have to do is we'll take the sum of the counts in our aperture, and that of course is very straightforward to do. All we need to do is just take our stamp that we cut out and calculate the sum. And NumPy will do all the hard work for us of adding all those numbers together. Do the same thing for our background aperture here. We have our BG stamp that we defined. We'll take the sum of that as well. And then we can see how many counts we got in each of these. So our target has almost 1 million counts in it. Our background has 600,000 counts in it. So you can see that there is more in our target aperture from that star. How many more? That's what we want to measure. So all we have to do is we'll take our target counts and we'll subtract off our background counts, and there we have it. So there are about 340,000 counts that we're getting in that box aperture from that target. Okay, so that's almost a measurement. To make it a measurement, we need to get the uncertainty of that. So let's look at how we can do this. First thing we have to remember is anytime we're looking at uncertainty, we got to start with uncertainty propagation, error propagation if you like. So we're going to use some version of this formula here. We're going to be taking our function, taking our partial derivatives and multiplying it by the uncertainty in each one of those terms. So what is the equation that we just did here to get those total counts? Well, it looks something like this. I've broken this up into 3 different parts. And you'll see throughout this tutorial why I did it this way. But we have one term, which is the source brightness for each one of those pixels. For the ith pixel, we take the number of counts we're getting from the source, add that to the number of counts we're getting from the background, right? Because that's what we're measuring in that stamp. That stamp has background light and it has source light all mixed together. So we're measuring these 2 terms, and then we're subtracting off of that the average sky value, the average background value, right? And we do this for every pixel. So what we have is we have 3 terms here, and we need to figure out what our uncertainty is when we have all these 3 terms. So it's going to be the sum in quadrature of 3 uncertainties. We know for that from uncertainty propagation. So let's start with the background. So first of all, this average background here is just computed by taking all of the background pixels in that square background aperture that we cut out and adding them together, just summing them all up, and then dividing by the total number of pixels in there. So I'm saying we have m pixels in the background, and you divide by that, and you get the average value, b bar here. Now it happens that we picked a background aperture that is the same size as our target aperture. So n here, this is the number of pixels in our target aperture, is the same as m. But it doesn't have to be. Note that we could have picked a bigger background, and we could have just computed the average and scaled it to the size of our n pixel aperture easily. And it's actually, that's a better way to do it. Usually you don't want m to be anywhere near n, and you want this to be a much bigger value, so you'll see that this makes this uncertainty in this term go away. But for now, we have these 3 terms, so we have to count the uncertainties in those. We can do this for the background pretty easily. We have that sample of background pixels, and if we want to know what the uncertainty is in that, we can just find out what the standard deviation of that sample is. And that'll give us a measurement of the uncertainty from the background. For the source, that's the tricky one. How do we know what the uncertainty is in our measurement of the source? Well, if we assume that we have a Poisson distribution, this is an important step. Right? We're getting light from a distant source. It's coming in kind of count by count. We're going to have a Poisson distribution. If we do that measurement many, many times, we're going to get a Poisson distribution. And so what is the uncertainty in the Poisson distribution? Well, we know this. This is the uncertainty, or at least the variance, is equal to the expectation value. So if we do this measurement many, many, many times and we take the average value, that is giving us our variance, our standard deviation squared. So we have our answer there. We've got some measurement of what we think our source counts are, so all that is what the variance is. So we can put this all together and use error uncertainty propagation, and we can see that the uncertainty in our total number of counts is going to be the square root of the sum of the source counts plus the uncertainty in the background times the number of pixels in our aperture, or n pixels in that aperture, right? Plus the uncertainty in our average background value multiplied by the number of pixels squared divided by the number of pixels in the background. So if this term isn't clear to you, you should use a little error propagation just on that final term there and derive this. But you can see from this that the larger our background aperture is, the smaller this third term is going to be. And that's why you usually want m to be much larger than n. So this kind of goes to a small number. You can also see that the larger your aperture is, the more noise you're going to have in it. So you got this uncertainty from the background, and that increases with the number of pixels you include. So we can put this all together now, and we can actually measure this. So we take our object variance is just going to be given by our counts, and actually we need to subtract off the background counts from that. So we just have the object counts. So this is the counts in our aperture, which includes source and background. We'll subtract off our background counts to get our object variance. Then we'll calculate our background variance just by multiplying the standard deviation of each one of those measurements by the number of pixels we have, and that's just the stamp size here. And then we have this third term here, which is the uncertainty in the background. So remember, we're subtracting off this average background from every pixel. So if we have any errors in that average value, and we do, then that's going to contribute to our total measurement uncertainty. So we have to include this term formally. And so then what we do is we'll add these three together in quadrature, and then we'll find out what our total uncertainty is. So we had something close to 1,000,000 counts, and you can see we're actually getting an uncertainty which is around 1,000 counts. And you can see how this is divided out, how it breaks down into those three components. So actually most of them, they're actually all contributing pretty much equally. Our object uncertainty count, the uncertainty counts due to the object Poisson noise, due to the background Poisson noise, and due to the uncertainty in the average are all about the same here, which is not ideal. And you can kind of see this is being caused by the fact that we have this square aperture and we're including lots of background pixels that really don't contribute to our signal at all. So we can do better than this, and that's what we're going to do in the next phase here. So first thing I want to do is I'm going to define this function here, plot example star image. And what this is going to do is it's going to load this example data. This is just a simulated image of a star, a tiny image. We're going to load that in and we're going to plot it. And then we're going to label the values for every one of those pixels. So this is that image that you saw at the beginning. And then later we're going to actually have some tools here to plot an aperture around it to show how we can do better than a box aperture. But we'll get to that. So I'll run this, and then we'll run that code. And here we go. So you can see now we have our image here, and we have these pixel values on here. Remember, this is just a simulated star. This is not the star we were working with previously. This is a different one. But this gives you an idea of what's going on here. So most of the light from our target is coming from this little patch here. But when we have this box aperture, we're including all these pixels way down here that really don't contribute much to the don't have much contribution from the object. These are dominated by the background level. So that's not ideal. What we want to do is we're going to just focus down on these pixels here that are dominated by object light and use those to determine how many object counts we get. And then we'll have less noise. All right, so what we're going to move to now is instead of doing box apertures, we're going to do circular aperture photometry. And this is very commonly used in astronomy. Box apertures are not very popular. Circular aperture photometry is. So all we need to do here is just sum up the light inside a circular aperture instead of a square aperture. All right, so we'll take a look at what that would look like. We'll show this example here. So instead of adding up all these pixels here, we're just going to add what's inside this red circle here. Okay, so what we can see is there's a few important things we have to consider before we can do this. One is we have to figure out where do we want to center the circle. Where does this go on this image? Probably here would be a bad choice. Here is a reasonable choice. We need some way to pick where we're going to center it. Second thing is how big do we want to make this? What's the radius? Like this seems like a reasonable radius. Should we make it a little bit bigger? Maybe. Should we make it huge? No, because if we make it too big, we're going to start getting noise in again. So how are we going to figure out how big to make that aperture? And then we have this other problem of how do we actually go about measuring these counts. So we have these pixels here. These are all nicely contained in our aperture. But then we have these pixels on the edge here where they're split. So we have to figure out how much of this light, if any, are we going to include in there. All right, so let's start with the first of those issues. Let's figure out where we're going to center our aperture. And we've talked about this before. We have this concept of a center of mass, or a intensity weighted center more generally, that we can use. So what we'll do is we'll just find where that center of mass is for this target using the brightness of each pixel as the mass or the weight for them. So what we do is we'll define our weights just using the values from our pixels. So the weights are just going to be given by the stamp values. And we're going to subtract off those background values. So we're going to take the NumPy median of our whole stamp just to get a value which is not weighted by those background values. And then we need to calculate what the center of mass in the x-coordinate and the y-coordinate are. So we're going to use these indices from the stamps. Remember, this is going to be values 0, 1, 2, 3, 4, 5, all the way up to however many rows and columns we have. And so we can just take those numbers and we will multiply them by the stamp values, the weights actually. All right, we'll take this value and we want to take a sum of that. So we use NumPy sum all those up, and then we divide by the sum of the weights. Right. And that gives us the weighted average x value. And for the y value, it's very similar. We just use the y-ins instead. Okay, so now we can run this, and it'll tell us that our object is centered at this pixel. These are on the stamp coordinates, so keep that in mind. This on the stamp, it's around pixel 9 in x and y. All right, so let's take a look at what this looks like. This is just to plot it up. And we can see we've put a red X there where our center of mass is. And so that looks like a reasonable value for the center of here. Now, this is not the only way, this is not even the best way to determine the centroid for an object. This is just something we can do quickly here. There's more advanced techniques for doing this. But doing a centroid like this is a good way to start. All right, so the next thing we have to decide is how big do we want to make this radius? Now, something we have to appreciate is that the light from each one of our stars is actually going to be smeared out on our detector. It's not going to fall on a single pixel. It's going to be blurred out in some area. And the reason for that is twofold. The light from our object could be the light from our object could be blurred by the atmospheric seeing. That's kind of the most important thing if you're observing from the ground. But even if you're observing in space, you can still have diffraction from your telescope aperture, which is going to blur out the light from your target. And then on top of that, of course, you could have an object which is some observable angular size. Now, for the star we're actually measuring, I want to keep in mind that stars, the actual angular size of the stars is much, much smaller than a pixel. It's like maybe 1/100th or even smaller than 1/100th of a pixel. So the light we're seeing is mainly being spread out by the Earth's atmosphere. So we're going to have to figure out how we want to account for that and measure the light from the star. And the way we're going to do this is we're going to start by looking at a profile of the object. So we're just going to take that two-dimensional stamp and we're going to sum it down just along one axis. And then this will just give us a one-dimensional profile, the average, the sum over all of the rows. And we're going to take that profile and we're going to subtract off the minimum value, just so we have values that go to 0 at the minimum. And then after we've done that, we're going to divide by the maximum value, just so we have values that go from 0 to 1. And if we do this and we plot it up, this is what we get. So here's our one-dimensional profile that we've averaged over. So the average over each row, and this is what we get. So you can see that the light is peaked in the middle and it falls off, but notice that it doesn't go to 0 at the edge. Well, I mean, it goes, one of these sides goes to 0 because we defined it that way, but you can see that the farther and farther out you go, it drops off, but it doesn't sharply drop off to 0 at some point. The light from the target is actually blurred over many, many pixels. It's blurred over a large area. So if we try to measure all the light from this, we need a huge aperture, and we're going to have the same problem we had with the box aperture before, where we're going to get lots of background pixels. So what we need to do is decide on a smaller area, maybe just measure this part here, where the light is dominated by the object light, and just use that to determine the brightness of the star. Now you may be saying, well, how come we're doing that? We're not getting the total light from it. But this is actually okay for photometry, because we're going to be doing we're going to be measuring the brightness relative to the brightness of other objects in the same image. So if we have another image and we measure the same fraction of light, maybe it's not 100%, maybe we only measure 90% of the light, but if we measure that for both objects, then the relative amount of light we're getting from those two objects will be preserved. So that's all that's key here. So we're going to pick a size where we're going to measure most of the light, so we're going to get a good signal, but not so much that we're getting background noise. So we have to pick how big we want to do this. And a good number to start with, and we'll see why later, is the full half maximum. So we can see from this the full half maximum it's going to be something about from here to here. So remember, the full width at half maximum, you go from the top to the half width to the half, and you want that full width there, which is about 4 pixels. So we're going to say the full half maximum is 4 pixels. And we'll just plot up here a plot that shows you an illustration of that. So yeah, it's about 4 pixels, right? So this is obviously a rough way to do this. If you were doing this for a scientific paper, you'd probably want to have a better way to determine this than just eyeballing it like we're doing right now. But this will get us started for this tutorial. So we're going to have an aperture. It's around 4 pixels in radius, actually. So we're not just going to measure this part. We could just measure this, but there's still a lot of light over here. So let's, instead of just using a diameter of 4 pixels, let's use a radius of 4 pixels. So to see what that looks like, let's take this plot. I'm going to shade in the region that we're actually going to use. So we're going to use axis v-span, and we're going to take values that go from the center of mass minus the radius, which is the full half max, and the center of max plus the full half max. Okay, and we're going to make this, let's say, make it red, and we'll have it see-through. So we'll use alpha of 0.25 to make it transparent. So there we go. We'll plot the whole thing now. So you can see this is where we're going to be measuring the light from here to here. This part, we're going to integrate everything within that aperture. This is just a one-dimensional representation. We're going to do this in 2 dimensions, of course. So we can take a look at what that looks like using the actual image. But just for now, notice that we're not using the full half max as a diameter. We're using it as a radius. So now to see what that looks like in the 2-dimensional image, we can just plot this up here. So we're just showing the stamp, and we're doing our usual things to flip it around. This is how we were looking at it before. If we look at it on this scale here, you might notice that there is an appreciable amount of light we're missing here. But this isn't a lot of the light. We're just showing it in this way so that the central pixel values are all pinned at the maximum here. They're all white. So if we change the scale here, we can get a little clearer clear view here, and seeing that, yeah, we're still getting most of the light here. There is some outside of this aperture, but we're certainly getting the vast majority of it. Okay, so all that's left to do is now we need to sum up how many counts we're getting inside this aperture. So let's turn again to this kind of example star image that we had, and we're going to show that aperture again. So here's our aperture that we would use to measure this. And again, we have all these pixels that are completely contained within inside this aperture, and so we can just add all these up as we did before. But then we have these pixels on the edges here where the aperture runs right through it. and sometimes it runs from one end to the other, sometimes it goes from the bottom edge to another edge, and you get different fractions of light from each one of these pixels on the boundary here. You don't get 100%. So the question is now, how do we account for this? What are we going to do to actually add the light in this aperture? And what we decide to do is we're actually going to take the fraction of this pixel that is contained inside the aperture and just count that. So if you look at this pixel here, for example, there's 419 total counts in this aperture. There's a little bit of light that's not being included there, so we're not going to add that to our sum. So when we're adding the light inside here, we're not going to add 419. We're going to add, say, 402 or whatever it works out. We're going to add the fraction of light inside the aperture. So this is our rules. If our pixel is wholly contained within the aperture, then we're going to add all the counts. But if, say, 50% of the pixels in the aperture, then we'll just add 50% of the counts. And if it's 90%, we'll add 90%, etc. So if you look at this, you can probably figure out how to do this, but it's not easy. It's not easy to determine what the area here is of this pixel when you have this curve intersecting it at these 2 points here. It's not easy to figure out what fraction of that light is. So I'm not gonna make you guys do that. What we're gonna do instead is we're gonna use a package called photutils, this AstroPi affiliated package, which is gonna do all that for us. So photutils, we'll import that. And what we can do here is we'll define an aperture. We'll tell where we want the aperture to be located, how big we want it to be, and then we can actually measure how much light we're getting on our image in that aperture. So first thing we do is we define where we want our aperture to be centered. So we're going to use our CMX and CMY as before, and then we need to tell it what's the radius for our aperture. This is just a circular aperture that we're using from photutils. And we've already defined a full width half max, so we thought it would be a good radius for our aperture. So we'll put those two values in, and we'll define an aperture object. And then we're going to use the photutils aperture photometry function to actually do the measuring. So we're going to give it our stamp, and we're going to give it that aperture. And then when we run this, it'll actually take the values inside that aperture on the stamp and sum them up for us. And so we can see what it returns here. It actually returns this table object. It's a quantity table. And in it, we only asked for one position, so it gave us one output row. We told it where we want the X and Y to be centered. It just tells us back that the X center and the Y center are these values. But this is the value that we wanted here. This is the aperture sum. Adding all those fractional pixel bits together, this is how many we're getting there, about 377,000 counts. All right, so that's the number of counts that are inside that aperture, but that includes light from our target and also from the background. So we have to do something to remove that background light. So what we could do is we could actually just use that simple square box aperture background aperture that we used before, but we can do a little bit better. So what we can do instead is actually use a circular aperture, specifically actually an annular aperture. So we're going to have an annulus that we're going to define around our target, and inside that annulus, those are the pixels we're going to use for our background estimation. So this will be very local to the target. All right, so first thing we need to do is we're going to do a shift of coordinates here because our stamp was a little too small. So normally you wouldn't cut out a stamp and do this kind of stuff, but we did for this demonstration, and it turns out that our stamp is too small to actually measure this background annulus. You need a big sized annulus for measuring the background. So what we're going to do is we're going to go back to our original image for these measurements, and then so to do this we have to convert from our center of mass on the stamp to the center of mass on the image coordinates. And all we need to do for this is we'll take our center of mass on the stamp coordinates, and we're just going to add this x origin value which we defined earlier, and this is just the pixel value for the lower left corner of our stamp in terms of the image coordinates. So same thing for CMY, we're going to add y origin. All right. And so now we can go ahead and run this, and I'll show you what we did here. Okay, so now we're showing the entire image. We're just using image show to show it here. And we have this red aperture shown, where we're adding our counts from. That's where our aperture is going to go down. And what we want to put on here now is an annulus to represent where the background is. So we're going to use some of the pixels out here, and we have some choices for how we can define this annulus. But what's convenient to do is to start with an annulus that's about 4 times the fold half max to about 6 times the fold half max, and use those to define our background sample. So I'm going to go ahead and redefine this. I just cut this line here and pasted it, and we're going to define this to be our background inner radius. And so instead of having a radius as being just the fold half max, we're going to have it be 4 times the fold half max. And then we'll have another radius, which is going to be the outer radius for annulus. And this is going to be 6 times the fold half max. And so now we can just add these patches to our image to see what they look like. And instead of making them red, let's make them blue. And we'll have our background inner. Cut and paste that, and our background outer. And there it has it. There you have it. So this is our inner annulus radius, this is our outer annulus radius, and the pixels that are in between these are the ones that we're going to use for determining our background. Now you can see that the width of this is the same as the width of our target, the diameter here of our target aperture. But if you think about it here, this goes all the way around this huge radius here. So there are many, many more pixels in this aperture than there are in here. And this is going to help reducing the uncertainty in our background average. So this is a good size for doing that. There's many, many more pixels out here than there are in this aperture here. Okay. So what we need to do is actually get those pixels. We have to define them so we can get what their values are. So we need to collect them somehow. There's different ways to do this, but one way to do this is just find all the pixels that are within the outer radius and outside the inner radius, just by calculating the distance from the target center to every pixel on the image. So I'm going to use NumPy indices again. And I'm going to pass it our whole image shape. So we'll get every pixel on the image, the whole big image now, we're going to get an x value and a y value. And then we're going to calculate the distance. So we're going to use NumPy square roots. Just a Euclidean distance calculation here. So we're going to take the center of mass and the x-coordinate on the image, so that's x2. We're going to subtract off the image x values and square this difference and add it to the center of mass y values on the image less the image y values, the pixel values, squared. And this will give us the distance from our target center to every other pixel on the image. And so then if we want to find which ones are in our background, all we have to do is ask for the distances that are greater than 4 times the fold half max, and that are less than 6 times the fold half max. And so our background sample is just going to be the pixels on the image that are inside that annulus. And what we can do now is, just to be safe, there might be some other objects that happen to fall in that annulus. And there might be another star, for example, that's nearby and might just happen to contaminate that annulus. It's not true in this case, but in general what you want to do is be careful, and you want to clip the background pixels so you remove those. So we're going to do a sigma clip. Just run sigma clipping on those image pixels and just return a sample of pixels that have outliers rejected. So we've defined that now. And so now we're actually ready to do the photometry with the background subtracted values. And the way to do this, there's different ways to do it, but what we'll start with here is just take that stamp, and for every pixel on that stamp, we're going to subtract off the background sample mean value. So subtract off the mean value, and then we need our aperture where we're going to measure this from before, and then we're going to print out how many counts we get, and that's in our phot table, our photometry table, the first row in the photometry table, and we want the column that is called aperture sum. So we'll print out how many counts we get after subtracting the background, and we see we get 305,000 counts inside that aperture. Okay, so we've got now a measurement of our circular aperture counts. One thing left to do is get what the uncertainty is. So we did this very, very similar to how we did it before. We take the counts that we got from the object. Remember, this is our aperture from our phot table. So we'll take our phot table, the first row, and take that aperture sum. And then we have to figure out how many counts we have from the background. So we can still take what the variance is of our background sample, but we have to multiply that by the number of pixels in the aperture. And we could just do pi r squared here to figure that out, using the full half max as our radius. But more generally, we can use a method in aperture called area. So we'll just run this function here, and this will return the area of that aperture. So this will work here. It's very simple calculation for our circular aperture, but we could have used a more advanced aperture, elliptical aperture, or really any other shape. So this will give you a more generic measurement of what that area is. But it's just the number of pixels inside the area. And it's a fractional number, remember. It doesn't have to be an even number. And then we're going to do, as we did before, define the background variance. And for this, again, we need the size of the aperture. The background uncertainty increases with this aperture. And we're done. So now we can see that the total uncertainty has dropped significantly. It's down to 584 counts. Remember, it was 1,000 before. And we can see what the contributions are now from these different sources. So before, they were all pretty much equal, but now this is not the case. Now our uncertainty is dominated by the Poisson noise of the target, which is what you want for a bright target. The background noise has been greatly reduced, and the uncertainty in the background, since we're using a larger background aperture now, that annulus, has gone way down. So we're in a case now, we have a nice bright object, and the uncertainty is just dominated by the Poisson noise. So there's a lot more to consider when you're doing photometry. We can use this photutils package for doing aperture photometry. There is some documentation online that I suggest you check out that tells you some more tricks that you can do, defining apertures that are not just in pixel coordinates, but you can also define them in sky coordinates, RAs and DEX, which is very handy to do sometimes. And so you should look through this and play around with it and enjoy.